ISTB presents, in association with Dhanmanjuri Community College, DM University, Imphal, launching a series of educational programs, recorded online classes for undergraduate and postgraduate students by teachers from various colleges and universities. During this COVID-19 lockdown, every day on ISTB Nongin, 8 p.m. from 24th May 2020 onwards. What's for Dept? Only on ISTB Nongin.
Welcome everyone. I am Keisham Nanao Singh of Manipur College. So today I am going to give a lecture which is that is on the topic spin-orbit interaction, and this is related to BSc Physics 4th semester. So before starting this topic, let me recall you some of what you have learned earlier. You see, an electron has got its own intrinsic spin angular momentum, and this is an intrinsic property. Just like that, you have electron has a mass, charge, so just like that, an electron has a spin angular momentum, and which we usually denote it by small letter s vector, and is given by under root of s into s plus 1 times h cat, where this s, small letter s, is spin quantum number. Spin quantum number, and whose value is half. And we also know that the magnetic spin quantum number of this electron is either plus half or minus half. Now, we know that an electron has got its own intrinsic spin magnetic moment, usually denoted by this symbol mu with a subscript small letter s, and this is equal to minus E by m times s vector. Okay, so in order to understand this spin-orbit interaction, we'll see this in the atomic physics concept, because the same term spin-orbit interaction also occurs in nuclear physics. But what you find here is that in atomic physics, you will get a more relevant nature to physical thing. So what spin-orbit interaction is that? Spin-orbit interaction is the interaction of the spin magnetic moment of the electron with the magnetic field that is experienced by the electron in its own rest frame. Or you may also say that spin-orbit interaction may be as the interaction between the spin angular momentum and the orbital angular momentum of the electron. So in order to understand this physical picture, let us see one thing. See, in the left frame, electron revolves around the nucleus, and which I have shown it here by the red circle. But when you just imagine that there is a person or an observer in the electron rest frame, what the electron will see is that this nucleus is orbiting in a direction opposite to that of that electron. This is equivalent to an electric current loop, and we know that an electric current loop produces a magnetic field, and this magnetic field produced at the side of this electron interacts with the spin angular momentum of the electron, and this is the physical origin of the spin-orbit interaction, which you can easily see from classical physics that is given in this atomic physics part. So this is what I have to say. So we are going to see the derivation of this expression for the spin-orbit interaction and this consequent energy. So this is the classical pictures what I have said just right now. Okay. So let me skip over some of these things. Now, For deriving this expression, we'll just consider small v vector to be the velocity of the electron, and in electron rest frame, the speed of the nucleus will be a minus v vector. So we know that the magnetic field that is given by this equation 1 is here. This is an expression you see from electromagnetic theory. So this magnetic field that is experienced by the electron due to the nucleus that is orbiting around it is given by this expression minus v cross E, where minus v is the velocity of the nucleus as seen by the electron, and this c is the speed of light, and this E is the electric field that is produced by the nucleus. And this electric field can be determined from this expression that is given in equation 2 here, that is given in equation 2. So E is equal to minus dV by dr unit vector r cap, and when you express it in terms of vector, the right hand side that you get here is minus 1 by r times this E vector, you get it to be the right hand side minus 1 by r dV by dr r vector. And this V is the potential which is given by the potential of the nucleus, that is given by ZE by 4 pi epsilon. Now, you insert these values of B, or you can say, first let us insert these values of E in this expression for magnetic field. And what you get here is that the last one, magnetic field, that is experienced by the electron is ZE by 4 pi epsilon naught times 1 by m c square r cube L vector. So this is the magnetic field expression that has been experienced by the electron. So, and what I am recalling is that in this this L vector, we are using this classical mechanics definition, r gross mass times velocity. This is the one where m is the mass of the electron. Now, the spin orbit interaction energy is E. I have used this symbol ELS, and it's minus mu s dot B vector. Why I'm using it is that you know that there is a magnetic field, okay? There is a magnetic field, and there is a magnetic moment mu s vector, and we know that when a magnetic dipole moment is placed inside the magnetic field, there will be a magnetic interaction, and that interaction energy is given by this expression. So this is what I'm using it here. Now, we insert these values of this B vector, mu s, which we have earlier given it here. So inserting this, we get this expression for energy as like this, 1 by 4 pi epsilon naught ZE by m square c square r cube. I think this should be 1 E square should be here. Okay, times L vector dot S vector. So this is the thing, and that I've given it as equation number 5. So up to the derivation of the equation 5, we were using non-relativistic case. So in the present case, what we have to do is that we cannot neglect this relativistic effect. So when that relativistic effect is considered, what happens is that there is an angular precision that is associated with the angular rotation, and this is known as Thomas precision, and this is related to cell theory of relativity. Okay, so the effect of this Thomas precision is that the magnetic field that is seen by the electron is actually not this, but it should be half effective. I call it here, I'm not given a symbol, but it should be half times what we have given here of this value in. So this is the thing, okay? So when this correction is met, the spin orbit interaction energy becomes as, here I have used a symbol EA. Earlier we used this symbol. So this is the thing that we get when relativistic effect is considered. Here, what is this value L dot S is given, can be calculated like this. For spin orbit interaction, the angular momentum L vector and the spin angular momentum combined by this L vector dot L plus L vector is equal to J vector. So when you square it, it is like this: L vector plus S vector dot L vector. So on simplification, you will get an expression like this: L vector dot S vector is equal to half times J vector dot minus so you insert these values, and this relation you have known that, or I can write it instead of this. You can also write this J vector dot magnitude square, L vector magnitude square, S vector magnitude square. So this is the thing. So on putting it, you'll get an expression like this: J into J plus 1 minus L into L plus 1 minus S into S plus 1. And we know that this J is your total angular quantum number, okay, and whose value, you know, it is given by this one expression. I think you must have learned this thing in your earlier class, okay. So anyway, we'll not go much, but we'll put on these values here, and another expression which I have missed out here is I square, okay. So this is the thing, because we you know that, for example, you can see it from S vector. So when you square it, you'll get S into S plus 1 I square. So like this, that is the thing that we get it here, okay. So putting this value, and another thing is that for the final thing, we have to use this expression, and for that calculation we cannot do it because this is not in your present syllabus. What we have to do is simply we have to use the result, and the result is that the average value of this quantity, that we have to use it. We'll take it for granted, okay. So that value is given by this one, Z cube, this is cube, Z cube, N naught cube, N cube, L into L plus half, L plus 1. This is the thing, which we get it from quantum mechanics, okay. These results that we are going to use it. Now putting these values and this value of this L vector dot S vector. So putting these two values, the final expression for energy is of the form which I put in this short way, that is 1 by 2 times R Cs alpha square Z power 4 into J into J plus 1 minus L into L plus 1 minus S into S plus 1 divided by N cube L into L plus half L plus 1. So this is the thing, where this R is the Rydberg constant that I have given it here, okay, this red one, last one, and then alpha is your fine structure constant, okay. So what you find here is that this interaction energy depends on Z to the power 4. So this spin orbit interaction is more important for heavier atoms. When Z increases, this will be more important. So let's see this one. So another thing that I have to say is that we can also express it in terms of terms values that which those spectroscopists used to use it, and that is a definition that I've given here. It is defined as like this: del E Ls by IC, okay. So this is the thing, when you put it, the thing that you get here is given in equation 7, where I put it the constants to be minus A by 2 J into J plus 1 minus L into L plus 1 times S into S plus 1, and this A I made it so equal to this one, so that's just to make a simple thing that we are putting in, okay. So this is the thing. So you can study this in terms of the term values which spectroscopists used to use it. Now, we'll go straight to this final one. And the thing is that in terms of energy, we can also study like this. If En denotes the energy that is being calculated from Bohr's theory, then the total energy that you get it after correction of this spin orbit will be, let us say some number ls, okay, will be like this. This is due to the energy calculation that is due to Bohr's theory, and this is the correction that is made due to spin orbit interaction. So for understanding, I'm giving an example here. Let us say these two states, 2p, there are two states, I call it 2p, this one, 2p 3 by 2 and 2p half. So I'm taking these two states. These two states have the same energy called En as calculated by Bohr's theory. So for that value, how it comes, let us try to understand in this way. For this first state, 2p, I'm taking this one, 2p half. Here, L is equal, we are using the symbol L, P. That is the meaning of L is equal to 1. Okay? And J here, J is this half. This is the value for J. And the symbol that I'm using here is for atomic states that are being denoted under LS coupling scheme. So this J is half. Okay, so putting these values of L, S, and another thing is that we know that S is equal to half. Now putting this L, J half in the expression for that energy, and what we find is the correction energy due to the spin orbit interaction is, I have used the symbol, this one in this slide. It comes to the order of minus ICA. Okay, so this negative energy means the energy is down. From the original level, the energy is down. So this was the earlier level, and this is the energy. I call it energy. I have given the symbol E1. Okay, so E1 is equal to minus ICA, and this is the thing that energy goes down, and this is the thing when spin orbit interaction energy is given, the energy level shifts down. And for this case of 2p 3 by 2, 2p 3 by 2, here L is equal to 1, as this is p, and here J is equal to 3 by 2. This is the value of J, and S is equal to half. Now you put these values in the expression for energy correction, then one find the energy level to be energy correction. I call it E2. Yes, this is called ICA by 2. Okay, so this is the energy level that is shifted by ICA by 2. Okay, and this is the level that is shifted down by minus ICA. So this is the thing that you can easily understand, that when spin orbit interaction energy is considered, the original energy level that is given by Bohr's theory gets shifted from its initial level, one up and one down. The upper one is your higher quantum. This is the state, and the lower one is this one. So you can see this from this slide. Here I have shown this one. This P state is the En. I have denoted that En, the blue one, is the energy level that is given to this Bohr's theory, and the red one, that is above one, that is the energy level for the state 2p 3 by 2 when spin orbit interaction energy is added, and the last line, that is green line, that is for 2p half state. So with this like this, you can also serve as an example problem like I have given it here, 2D. For this two state, you do it yourself, and 2D 3 by 2. So for these two states are initially same energy level, but they will split under spin orbit interaction. So this part you can do it as an exercise. Okay, that's all for today. Thank you.
ISTB presents, in association with Dhanmanjuri Community College, Dept University, Imphal, launching a series of educational programs, recorded online classes for undergraduate and postgraduate students by teachers from various colleges and universities. During this COVID-19 lockdown, every day on ISTB Nongin, 8 p.m. from 24th May 2020 onwards. Watch for that. Only on ISTB Nongin.